So, so one of the things I'd like for you guys to know is the IMFs. And IMF stands for intermolecular force. All right, so really quickly, ionic would be, what would it be, the strongest or the weakest? Okay, so what type of boiling point would it have? Okay, we would expect this to have the highest boiling point. Okay, next on our list would be, let me get a pen that writes. Next highest on the list would be, now both of these are polar. Both are polar, but there's a special type of polar. What is that called? Okay, this is called hydrogen bonding. And we would expect that to be stronger, though it's not ionic. And then this is also polar. It's dipole-dipole. This is also dipole-dipole, but it's hydrogen bonding. And then what's next? The weakest on our list is dispersion. Okay, so we would expect this to have the lowest boiling point. So what type of molecules are dispersion? What class? There's a functional group that I want you to associate with dispersion. And what's the name of that functional group? The alkanes. So what are some examples of alkanes? Methane, ethane, propane, okay, butane, okay. And then what other molecules are also held by dispersion? Okay, nonpolar molecules. What is an example of a nonpolar molecule? Okay, some molecule, it has an electronegative atom. You know, what are electronegative atoms? You know, like your halogens, your chlorine, oxygen, fluorine. These are electronegative, so they pull on this bond. Okay, so it's not a equal 50-50 sharing of this covalent bond, but instead they pull disproportionately, making it partial negative. Okay, but why is this nonpolar, even though they have the pull? Okay, they cancel each other out. Doesn't the up cancel with the down and the left cancel with the right? So this is nonpolar, and the alkanes are nonpolar. So these are held together by the weakest force. This weakest force is known as dispersion. Okay, so alkanes. Okay, also the alkanes that we studied in this class are also known as the hydrocarbons. So the highest boiling point would be ionic. So what would be something that's ionic? If you watch the video, sodium hydroxide, sodium chloride, yes? Calcium chloride, metal with nonmetal. Are these examples of ionic compounds? Yes, is correct. What is an example of something with hydrogen bonding? Okay, we look for three things. We look for a hydroxyl group anywhere in the molecule. We look for anywhere in the molecule an NH group or NH2. This is called an amine, but it's okay. You don't have to know that functional group called an amine. And we look for a fluorine anywhere in the molecule. Okay. So this is dipole-dipole. This is polar, but it has a little extra strength and makes it a stronger intermolecular force than just plain old normal dipole-dipole. Okay, these two are called polar. Okay. All right, so the highest boiling point will be ionic. Okay. What about the delta H vaporization? Okay, which would have the highest and which would have the lowest? If you were to rank these, which would have the highest delta H vaporization? This delta H vaporization is the energy required to vaporize 1 mole of the substance. Ionic would have the highest? Correct. Okay. Energy to vaporize, convert to a vapor. Okay, 1 mole. And this is in kilojoules per mole or joules per mole. Okay, so which would be the highest? Did you say it, Susanna? Yes, the ionic would be the highest. And which would be the lowest? Dispersion, okay? You saw this in the lab, okay? You saw this. I saw it with my own eyes. I held your filter paper, the pentane, the filter paper that was soaked in pentane. I felt it in your lab groups. It was dry. You know? It was drier than this piece of paper, okay? The pentane and hexane, which are alkanes, and they just go, okay? And then we have everything kind of in between here. Okay, which would have the highest vapor pressure? Very good. This would have the highest vapor pressure. It takes very little energy to vaporize, so obviously it will vaporize. So any vapor also means it can exert a pressure. And which would have the lowest? Ionic. Okay. All right, so can you name me some ionic compounds? I already gave you a couple. What's some? What are some examples? Sodium chloride, sodium hydroxide. Okay, what are we looking for here? A metal with a non-metal. Okay, a metal with a non-metal. Okay, so an example of ionic would be look for a metal, look for a non-metal. Okay. And what is the name of this functional group? Which one? Alcohols, okay? So it's not methane, ethane, propane, hexane, so on and so forth. This would be methanol, ethanol, propanol, butanol, so on and so forth. Okay? So these are the ones that can hydrogen bond. All right, the more OH means what? More hydrogen bonding, higher boiling point, also higher viscosity. Okay. So more OH, if there's more OH decorated around the molecule. Okay, OH is called a hydroxyl group. Okay, for those of you taking organic chemistry next term, OH means hydroxyl. And OH minus, for those of you that should know this, you've taken Chem 1, this is called a hydroxide ion. Okay. So this bound to some, whatever, we don't care about the atom here, X or R. Okay, that's the hydroxyl group, the OH bound to something. But the OH minus is called a hydroxide ion. Okay, this is something you should know, hydroxyl group. You don't have to know that, but it's actually good to know. I should say you should know that. All right, back to this. So if there's more hydroxyl groups around the molecule, okay, we've already established that it can hydrogen bond, but more OH means more hydrogen bonding potential. Okay, more hydrogen bonding potential means higher boiling point. And higher boiling point also means another thing that we talked about, and that means more viscosity. Okay, we gave an example of a molecule known as glycerol. More viscosity. Okay. So this is the path that I want you to know, the pipeline. Alcohols have OH, but if there's more OH around the molecule, there's more hydrogen bonding potential. More hydrogen bonding potential. Higher boiling point. More viscosity. Example is glycerol. Okay, how many of you have ever purchased glycerol from the CVS or the Walmart? Have you? Anybody? Nobody has, but you can go to the CVS section or the, Walmart or wherever, and you can purchase glycerol, I believe. Okay, and this is very viscous. Okay, why is it viscous? Okay, let's draw the structure of glycerol. This is the structure of glycerol. Would you think glycerol will be viscous or not viscous compared to, I don't know, an alkane or water or something else? What do you think? Viscous? Yeah. And compared to some of the other molecules, this is very viscous. Why is it viscous? Because of these OH groups. Okay. Okay. If any of you have taken biology, there's something called the extracellular matrix. How many of you have heard of the extracellular matrix in biology? So the extracellular matrix has a lot of these molecules like hyaluronic acid or chondroitin sulfate. These are also things you can buy from the vitamin store. They make your extracellular matrix viscous. Those are the type of molecules. Why are they viscous? They have a lot of OH groups around them. They have a lot of NH groups around them. So the idea, just for this exam, more OH, more viscous. Okay, more OH, more viscous. Alright, so we should know our trends here for the different intermolecular forces, their effect on boiling point vaporization and delta H vaporization. All right, which had more dispersion forces in the lab, hexane or pentane? They're both alkanes, but which one had more dispersion? Okay, why would hexane, Samantha, or Sam, why would it have more dispersion? Okay, so we have to realize that the more mass you have, the more dispersion forces have to be overcome. Okay, so this has higher dispersion forces. If you want to vaporize this, it's going to take more energy. If you want to vaporize this, it's going to take more energy. Why? Because this hexane is bigger than pentane, right? So more dispersion because more mass. More dispersion forces. All right, another question being asked is normal. What does normal mean? Okay, so if we plot the vapor pressure on the y-axis, temperature on the x-axis, what will it look like? Okay, the vapor pressure is a dynamic equilibrium between liquid and vapor. Okay, it goes back and forth. But it has this type of shape, the graph. If the vapor pressure is 1 atmosphere, which is the outside surroundings, and you plot it, hit it to the temperature, okay, if this is whatever molecule it is, let's call it water. Okay, and if it's 1 atmosphere, this is called the normal boiling point. And you're correct. Normal means 1 atmosphere vapor pressure, and for water, this happens to be 100 degrees C for water. And 1 atmosphere. So normal means 1 atmosphere.
if it's attached to an alpha carbon, that's not necessarily hydrogen bonding.
An alpha,
Where it says
yes, if it's
R
attached to a carbon,
but not necessarily an alpha carbon.
not necessarily an alpha carbon.
Can you give me an example of the RF? Because in my mind, it's like it has to be attached to an H or something.
Right. Yeah, this can hydrogen bond.
Yeah. So the R is not necessarily a carbon.
It depends on the strength of the dipole. This can hydrogen bond. This is a positive side. Fluoroamine, or yeah, this can hydrogen bond. And this fluorine is attached to a nitrogen. And fluorine is more electronegative than nitrogen, so that's partial negative. And this nitrogen will be partial positive. This nitrogen also pulls, so this will be partial positive.
But if it's a carbon there, that's not necessarily, because to me the NH qualifies for H bonding as well. So that looks to me like, yes, hydrogen bonding.
This would be partial negative. This will be partial positive. I don't think this can hydrogen bond. So you want an example other than carbon?
It's just a little confusing to me. Like when the only example I can think of is HF. That's the only one that I can think of.
I think there's other examples, but they're not coming straight to the top of my head. You need a hydrogen. So this will pull this way. And this oxygen will pull this way. So I think this is an example. HOF. OFH. I think that's an example of something that can hydrogen bond where it's attached to an oxygen. That would be an example. There's several more, but it doesn't have to be. You need a hydrogen to hydrogen bond. You're right. That's 100% correct. But that doesn't mean this is exclusively hydrogen. This can be some other electronegative atom as well.
The fluorine is attracted to another hydrogen on another
HOF molecule.
Okay.
Attraction means this is a partial negative and this is a partial positive. Yeah. This would not hydrogen bond because the carbon would be partial positive. Carbon doesn't have a lot of pull. It's mostly the halogens, which are group 7, oxygen and nitrogen. Maybe a little bit of phosphorus that I say have pulling power that make it polar. But HOF would be a molecule that has a fluorine and can hydrogen bond. And you need a hydrogen, obviously, otherwise there's no hydrogen bonding. That's one thing that I can think of off the top of my head. You can replace this R with another electronegative Cl. Fluorine is the most electronegative. They have numbers attached to them. I don't want to get too bogged down into it. But fluorine is very electronegative, so it can pull, and then you need an H, right? Yeah, anyways. One, two, three, four, five. 1, 2, 3, 4, 5, 6. Yeah, then we're starting getting to some weird looking molecules. But I think, to your question, I think it doesn't have to be a hydrogen. There's some other, this R doesn't have to be just a hydrogen. We give a hydrogen because it's the simplest explanation, but it could be other molecules that are slightly less electronegative. All right, let's move on here. So normal is 1 atmosphere. Okay. And this R can be hydrogen, but it can also be something else, okay? Not, yeah. Let's go ahead here. All right, so all the intermolecular forces, dispersion, I think I want to make this a point. Dispersion is an intermolecular force that's everywhere. Okay, so it's very weak, it's very transient, and all molecules have dispersion. But if you're looking at something like maybe a methanol or butanol or anything like a polar molecule, it's not the main one. So something like a CH3 would be dispersion, okay, as the main intermolecular force. But if you have a CH3OH, which is methanol, it would be dispersion. But what else would it be, or what's the main one? Hydrogen bonding, okay? By its nature being like transient and always moving around, these electron clouds, dispersion is going to be in every molecule. Even water will have dispersion. But we don't really say water has dispersion. We say water has hydrogen bonding. But it has dispersion, but it's just so weak. So hydrogen bonding is the main one, but it also has dispersion, but it's extraordinarily weak. It's not the main one. The main one is hydrogen bonding. Okay, what about for an ether? What's the main intermolecular force for an ether, like dimethyl ether? Okay, this is called the methyl group. This is something you don't have to know for this class, but so dimethyl ether, what's the main intermolecular force? Polar or dipole, but what else is there? Very, very minor. Yeah, so the point I'm trying to make is that every molecule will have IMF as dispersion as an IMF. But it's just that this molecule, the alkanes and nonpolar molecules, just have dispersion. All right.
Test me to write all three, or
just make sure you just make sure that there's also dispersion. It's ubiquitous, it's everywhere. But it's, it's not the main one, okay, except for the alkanes and the nonpolar molecules. That's all. And so we talked about 3 properties of a liquid. All liquids have this. Okay, can you name them for me? Surface tension, all liquids and not just water. Okay, when I say liquid, it doesn't just mean water, anything that's a liquid. And then what's the other one? Viscosity. Okay, we gave an example of having more OH groups, it will be more viscous. And then the 4 colligative properties, we hit this kind of hard these last couple of weeks. What are they? The new boiling point, and it's going to increase. Okay, very good. Okay, the equation for that, the new boiling point is going to be this. Okay, I'll give you this equation and the constant on the exam. What will happen to the freezing point? Okay, this is called freezing point depression. So the new freezing point will be this equation. You have to subtract because the freezing point goes down. What's the third one? Okay, vapor pressure lowering. Okay, so the new vapor pressure of this solution is going to be the mole fraction of the solvent times neat solvent. Okay, neat means by itself. And then what's the other one? Okay, osmotic pressure. Okay. And what are the units of molarity and molality? Okay, so these are easy questions, so don't get them wrong on the exam. What's the units of molality? It's not moles over something, it's moles of... Okay, you're going to write moles of solute over what? Don't write moles over kilograms. Okay, a lot of people do that. What do you say? Moles of solute over kilograms of solvent. Okay, that's one type of concentration. What's the other type of concentration? Okay, don't just write moles over liter. What will we write? What are we going to write? Over what? Liters of solution. Okay, these are important concentration metrics. These are important concentration determinants. How do we tell if something is concentrated or not? We use in chemistry molal and molar. All right, and then mass percent. What is the mass percent? Okay, so let's say we have 5% glucose solution. Okay, we'll do mass percent. It's a mass over mass. Okay, or mm. Now, in the denominator, you add everything. Okay, the denominator has everything. Okay, and let's say it's aqueous. Okay. 5% aqueous glucose solution. What does that actually mean if we were going to deconvolute this or make it? How will we make 5% mass percent glucose? Okay, so this means 5 grams of glucose. And again, when you say percent, the denominator has everything. So what is everything here? Right. And to make it a percent, you take this fraction and multiply it by 100. Right, so there's some additional problems here that I will not go over because it's extra credit. One of them is on osmotic pressure. You can choose to do that if you'd like. Another one is the heating and cooling of water. Okay, so I will not go over them because they're not counted towards this exam. So let's say we want to take water and we have it at minus 20 degrees C and we want to raise the temperature to 150 degrees C. If we're heating it, what will the sign of Q be? Okay, the sign of Q will be positive. Okay, and how will we go about doing this? Okay, so we're going to break this up. Okay, so we'll have Q equals ms delta T. And that's going to be for the first one, which is minus 20 degrees C to 0 degrees C. Okay, here we'll use Q equals ms delta T. Okay, and then you'll use the specific heat of water as solid. Okay, okay, I'll give you that. I'll give you that constant. S is specific heat. Okay, what happens at 0 degrees? Okay, so for the phase change of water, this is going to be delta H fusion. All right, so this will be Q1. This is Q2 heat. Okay, so delta H fusion. Okay, and this is for 1 mole. Okay, so if you're, so you make sure you convert your grams to moles. What will Q3 be? Zero degrees to what? To 100 degrees. Okay, so here you're going to use Q equals ms delta T. We're going to use the specific heat constant for water as water liquid. Okay, so that's Q3. And then what happens at Q4 if we're heating water from minus 20 to 150 and we want to figure out how much heat we need to add? Okay, what happens at 100 degrees? Okay, and what is the phase change for this? What will it be? Vaporization. Okay, and then finally Q5. Okay, finally we can go to 100 to 150 degrees or whatever the final temperature in the problem is. Here we're going to use Q equals ms delta T, and then this is going to be the S of water, the specific heat of water as a gas or steam or whatever it's. So to get your final answer, again, this is extra credit, so I'm not going to go over any of this. You add Q1 plus Q2 plus Q3 plus Q4 plus Q5. If this was cooling, what would the sign of Q be? Same value but negative, okay, because the heat is going to the outside. All right, so something like this, osmotic pressure, plug and play or plug and chug. And then we went over the computation problems in the previous lecture. All right, are there any questions or comments for me?
Question about ionic and dipole interaction. I know it's not part of the main core.
Yes.
What is this considered?
It depends on the nature of the ion. It depends on the nature of the polar molecule. So in the ranking, it will probably be around here. Yeah, it may be like a little higher than dipole or a little lower. It depends on the size of the ion and the dipole molecule.
The term solvation, does that refer to when it breaks apart in water, or it could be any solvent?
Water has the ability to break it into ions, not other solvents.
So solvation refers to
water.
Okay, making a circle around the broken.
They call it a hydration shell. It's making a hydration shell around the ion. So the water will hydrate the ions. So it makes it. Yeah, that's all I'm going to say, without getting into other things. Hydration shell or solvation shell. Anything else? All right, I'll see you all on lab if you're in the Monday lab, or I'll try to be in at around 1:30 to 1:45. For those of you that can make it. If not, please come after your 1 o'clock class.